welcome back to another lecture on development and applications of special concretes. Having completed the discussion on the review of proportioning of concrete mixes, today we will review our understanding of pores and porosity in concrete, and that's still a part of the review of normal concretes that we are doing as a part of the foundation for the course on special concretes. Now this is a picture which we've been seeing all the time, except that I've dropped all the descriptions, assuming that you've had enough of it, and I think now you understand the model that we've been talking about. But still we'll look at this picture once again today to understand this idea of pores and porosity. So what we are trying to do is we've modeled this concrete the way it is shown in this picture here. We have these coarse aggregates sitting here, and we have the mortar phase here. Now around this coarse aggregate and mortar, we've talked about this transition zone, and this is what we have called the main body mortar. Now if we look at a small part of this main body mortar here, the way it is expanded into this small inset, we have these as the solid hydration products, which we can call as hydrated cement paste, and we have these as pore spaces. Of course, it doesn't mean that there are channels of water running all over the place, but what it really means is only the fact that in HCP, the kind of products that we have are more dense, and in the pore spaces, these hydration products have a lot more water in it. With that understanding, and kind of assuming that all these pores are not necessarily of the equal size, let's start our discussion today. Porosity in concrete comprises of the porosity in aggregates and the porosity in the hydrated cement paste, which I have written it as HCP. Now we've already told you that these aggregates are also porous, except that the porosity of these aggregates is much lower compared to the porosity of the mortar that we create. We create means it's man-made. It is governed by the water-cement ratio. When I talk of mortar, I'm more or less always talking about cement paste in this context. And the discussion today focuses on revising our understanding of the porosity in hydrated cement paste using highly simplified models and schematic sketches. So even though we'll use the word concrete and cement paste quite interchangeably, we'll talk of the porosity in concrete, but please remember that the porosity of concrete basically has these two components, and most of the time we are talking about the porosity which is in the hydrated cement paste, because this is what we control largely as far as normal concretes is concerned, and it is this part which governs things like the strength, permeability, and so on. So we are really interested in the permeability or the porosity, the pore size distributions, whatever happens in this part, the hydrated cement paste. The porosity in aggregates is not something that we bother about all the time. So having said that, let's start our discussion and look at the hydration model of Portland cement. What this hydration model really tells you is that these are the cement particles. Of course, I've taken them to be spherical, but obviously cement particles are not spherical. They are highly angular in nature, but for the sake of argument, it's much simpler to draw perhaps. It's much simpler to take. There is a certain amount of particle size distribution as well. So these are the different kinds of cement particles. And this is analogous, or this is in line with our discussion that cement paste is a suspension of cement particles in water. So basically this part here is all water. Now once water and cement are in contact with each other, just as water comes in contact with the cement, hydration starts. And these hydration products or hydrates start to form. Now you can see that these hydration products or hydrates overlap at this point leave or catch some amount of water inside the different hydration products and so on. So it's a very complicated, complex thing happening within the concrete matrix. Having said that, we should also try to understand or remember that after all, the hydration of cement is a chemical reaction, and therefore there should be stoichiometry associated with it. What is the stoichiometry part of it? That is, we talk of any chemical reaction, zinc plus sulfuric acid giving you zinc sulfate and hydrogen gas. Now we know that how much of zinc will give you how much of hydrogen. How much of zinc will react with how much of sulfuric acid. Now if that is the kind of chemical reaction that we know about, then hydration of cement, which means the reaction of cement and water, that also should have a certain fixed stoichiometry, that okay, for hydrating 100 grams of cement, how much water is required? Now to answer that question, let's understand what cement is made up of. Cement is made up of 4 main complexes and they hydrate almost independently. Now this picture here tells you these 4 hydrates: the tricalcium silicate, the dicalcium silicate, tricalcium aluminate, and the C4AF, that is the tetraaluminopherrites. Now these fellows, all of them hydrate more or less independently. So if we go back to the previous model, we can say that okay, here is a cement particle, part of it is C2A, part of it is C3S, part of it is C2S, part of it is C4AF, part of it is C3A, and so on. Now all these guys, they start reacting with water independently, and each of them has its own heat of hydration. Now this heat of hydration, if we look at this table closely, at 3 days, 90 days, or 13 years, what it shows is that in the initial period, C3A gives out a lot of heat, and this heat can be looked upon as a proportion of what the total heat of hydration liberated from C3A in 13 years. Now you can see that 66% of that is liberated here, and more or less 90% of it gets liberated in just 90 days. This is not really true for something like C2S, where this 12 is just about 20% of this 59 or 60, and this 42 is just about 2/3 of this. So basically cement hydration continues for a very long period of time, and all our discussion of the 28-day strength and so on is just a model. It's an engineering approximation that a lot of hydration has taken place, and whatever strength development happens beyond that point is a bonus. Of course, in this discussion we are taking the heat of hydration liberated as a surrogate parameter to estimate the amount of hydration. So now if that is what we kind of agree upon, then let me also share with you that chemically the amount of water required for hydration is reported to be between 18 to 22% by weight of cement. That is, for hydrating 100 grams of cement, we need 18 to 22 grams of water. Now, of course, any reaction has 2 dimensions to it: completion and rate. When I say that it requires 22 grams of water per 100 grams of cement for hydration, I'm not talking about the rate, how soon it will be consumed, how much later it will be consumed, and so on. But let's take that with a pinch of salt and leave it at that and say that okay, the amount of water required for hydration of cement is between 18 and 22%. So having said that, the water added to concrete is far in excess of that required for hydration. Those of you who are coming from the field or who have some experience with concrete know that in concrete the water added ranges from about 40 to 55% in most cases, and that is what we call the normal water cement ratio. Now sometimes we use something below this, sometimes we use something higher than this, but this I think would be something like the normal range. Now even in this normal range we can see that these values are much higher than these values. Now what happens to this excess water that we add? It all remains in concrete after the hydration is over. Even if we assume that all this 20 grams of water which is required, or 20% of water which is required, is actually consumed, and all the cement actually gets hydrated, because at the end of it there is half a possibility that some part of cement does not get hydrated at all. So in that case, even that amount of water which would normally have been consumed in hydration, that also remains. In addition to that, we have added so much more water, and that is in any case going to be around in the cement matrix. Looking at this picture graphically, if we start with cement particles here, the amount of cement that is given here, we add a certain amount of water to it. At an intermediate stage of hydration, this is what we'll have. Some part of cement would have been hydrated. What this picture shows is that this amount of cement has been hydrated. This amount of cement is still remaining. Some hydration products have been formed, and there is some water still remaining. There is some volume changes that may occur due to hydration. We are not particularly looking at this right now. Let's keep it aside and let's keep moving forward. At the end of the hydration process, we can see that there is no cement left, and all the cement has been converted to hydration products, and this is the water which is remaining. This is the pore space. Now this total thing is what is giving you the total pore space, because this water also can evaporate out, can be moved out over a long period of time. So we'll try to see just now in a little while what is the nature of this water sitting inside the concrete. I just said sitting inside the concrete, but please remember, go back to that picture which I showed you. This water is sitting not with the aggregates, but within the hydration product somewhere, as we shall see in some of our model and schematic representations just now. Now this is the unhydrated cement. There's another possibility that if the entire cement does not get consumed, then we have some unhydrated cement as well. And this unhydrated cement, there will be some remaining water, that is excess water, there will be some total pores, hydration products. So this is what is going to happen. Having said that, let's look at this picture once again, that this is what we started with, this is what we have as an intermediate position, and what is this picture trying to tell you? This picture is trying to tell us the evolution of this part of our discussion. That is what is happening in this part, that is the mortar part or the paste part, where water started to react with cement, formed hydration products which are shown here, and led to some pore spaces which are shown here. Also keep a close watch on this picture, and we will come back to this picture in a while. Now let's take a numerical example. The numerical example says that if we have a water cement ratio of 40%, what does that tell us? That we have, let's say, 314 grams of cement. And for that, if we use 40% water cement ratio, we have how much of water? 125.6 grams of water. Now, assuming that the specific gravity of cement is taken to be 3.14, this 314 grams turns out to be 100 cc of cement, and that 100 cc of cement and 125.6 cc of water gives us a total volume of the paste to begin with as 225.6 and 439.6 grams. That is my mass. That is 314 plus 125.6. So this is the mass, this is the volume, and the game begins. The game in the sense, the hydration of the cement begins. If we assume, and let's do that, I mean, we'll have to make some assumptions. 25% of water by cement weight is needed for hydration. So instead of that 18 to 22%, I'm using 25% as the number. And we also assume that there is no change in the volume of cement paste during hydration. That's why I said that I'm not going to particularly consider or follow the small changes in volume in the cement paste as hydration proceeds. So if we're making this assumption, and if we do that, then this is what we will begin with. Cement here, water here, and what is going to happen finally is that 78.5 grams of the 125.6 will be consumed in the hydration of cement. We had 314 grams of cement, 25% of that will get consumed, which means that 47.1 grams of water will be left behind, this minus this, and that is the unreacted water and will eventually escape, leaving void space. Now, given the initial volume of the paste to be 225.6, the assumptions in the arithmetic, the hydration products will weigh 392.5 grams. That is the total mass that we started with minus the water that's going to escape or we allowed to escape. These fellows will occupy 178.5 cc of space. Now, if we understand this discussion, what it really shows is something like this. We have this as our HCP, and this is my 47.1 is what I'm talking about. Now, this amount of water is not necessarily sitting here and all of it will evaporate. No. For that matter, even this is just a model representation of cement particles surrounded by a certain amount of water. So what we did was we lumped all these cement particles into solids here and then allowed all the water to be coming here. So this is what exactly the model which we have used as far as proportioning of concrete mixes is concerned. We said, okay, all those particles, the solid volumes together will be put at one place, giving rise to that volume of coarse aggregate, volume of sand, volume of cement. Here also in the paste phase, this is exactly the model we are using. In real practice, this is what the situation is. That is, we have cement paste all over the place, and within this paste we have some kind of water which is available in different channels, if you want to use the word. That's exactly the picture that I showed you from that small part of paste. This is the water which is available all over the paste, and the total of this water is equal to the volume of unreacted water. And therefore, what I said about the hydration products and the water present within the hydration products at the final stage is also true at the intermediate stage. That is, the HCP here in the intermediate stage also has a certain amount of water sitting within the HCP. And it is the removal of this water from the concrete. Again, I'm using the word concrete. Strictly speaking, it is HCP over a period of time through evaporation and so on is at the root of the pores formed in concrete. So once again, look at this picture here. This picture here shows the model that we talked about, that this is my HCP which is over here, but the volume of this HCP is actually the whole thing here, and this water which I have depicted as free water available here is distributed all over the HCP here. Now all this business here is happening within this small element of cement paste which is expanded into this form. So this part, this picture here, A, is nothing but this picture B, which is shown here, with the pore spaces being shown what it is. Therefore, now let's try to take a closer look at this part. In the beginning of the lecture, I had talked about it, that please look at this picture carefully. We are going to come back to this. Now, what this shows is exactly this. Now, what is the nature of HCP here in this area, which is shown in the red part? That is my HCP in the ITZ. What is the nature of the HCP here? This HCP in the ITZ is different, is not the same as the HCP other places. What is the difference? The difference will be this kind of water which is present in the HCP in this neighborhood, that is in the ITZ, and this kind of water which is available or present in other places as far as the mortar of the HCP is concerned. So if we keep this in mind, the discussion or the understanding is much better. When we said that the water cement ratio in the ITZ is higher than the water cement ratio in the paste otherwise, what it means is there is more water here in the cement paste, finally, in the hydrated cement paste at the end of it also. Moving forward, this discussion that we've just had clearly establishes that the pore space in concrete or HCP will be higher in case the water cement ratio is higher. Obviously, when we have water cement ratio of 40% compared to a water cement ratio of 50%, for the same amount of cement, we are adding more water here. But the amount of water which will be consumed during hydration will be the same, and therefore this excess water will be greater if the water cement ratio is higher. The initial water cement ratio is higher. And that really is the root of the issue, that higher water cement ratios lead to lower strengths because there is a porosity involved in between. Higher water cement ratios gives you greater porosity, which has lower strength. And this lower strength part of it is something which is pertaining to the mortar. Remember that the aggregates themselves, their strength is not coming into play. I've possibly said that in one of the lectures before, that the strength of the aggregates as far as normal concretes is concerned is much higher than that of the cement paste that we use or the mortar that we use. This may or may not be true. It starts becoming a little difficult to defend this kind of an assumption as we go higher in strength, but most of the time it is true. And that's why the general rule that the strength of concrete is governed by water cement ratio is coming from this kind of discussion here. This is a picture which is taken from one of the research publications where the authors were trying to model chloride diffusion in heterostructured concretes by finite element method. Now, what they were trying to do was study the diffusion of chloride ions into concrete, and that was possibly being done by studying the diffusion of chlorides through the cement paste and therefore through the pores in the cement paste. Similarly, this picture here talks about the pore structure that we expect in concrete, and we have several types of structures associated. We have solid products, which is aggregates, unhydrated cement, and a bit of hydrated cement. There is chemically bound water, there is gel water, free water, and empty pores associated with the concrete structure. I hope you can see that this picture here is something very similar to the kind of model that we have tried to draw, possibly much simpler. And if you look at water alone, which is sitting inside the concrete, we have evaporable water and we have non-evaporable water. This non-evaporable water is the chemically bound water which is sitting with the hydration products. The remaining water, which was shown in blue color in those slides, was gel water and free water, and that is possibly evaporable and we can get rid of it. So therefore, this plus this gives me the clear pores. Gel water is a little more difficult to expel, but it is not chemically bound. So this is basically the entire cement paste part, the unhydrated. This part here is the cement paste. Hydrated cement, chemically bound water, and gel water within the hydrated cement paste. That is how we can model or we can understand what is going on in this entire body of concrete. So we have not only the aggregates which are solid, but some other things have also solidified. The hydration products are solids, except that they have some layers of water sitting in them. As far as some comments on the pores in the cement-based materials, let's try to summarize our understanding. Cement-based building materials such as concrete and mortars are porous with a complex internal pore system. Hydrated cement paste HCP contains capillary pores which have a large variation in size due to particle spacing of cement, the cement particle spacing in water and cement suspension. There are smaller gel pores which are the interlayer in the CSH or other hydrates. Spherical air voids and large diameter, which is greater than 20 microns, naturally or artificially introduced, are also present. So we are here talking about entrained air. Continuing further, in the neighborhood of the aggregates, a more porous ITZ is present, and that's what we talked about just now. Presence of pores is at the root of almost all durability related problems which can arise out of the ingress and movement of deleterious ions in materials through the pore space. So that's why we really need to have a very good understanding of pores and porosity in concrete. And that's why I thought that among the things that we need to review as part of our discussion here as an introduction to special concretes is a closer look, a relook at the pores and porosity and porous nature of the concrete. Concrete is not as solid as we may like to believe. With this understanding, let's try to move forward. Here is a distribution of pores in concrete as far as size is concerned. These are the 5-6 different types of pores that we have. We have entrapped air, entrained air, capillary pores, gel pores, and intracrystallite pores. Now, entrapped air, as far as size is concerned, this is the diameter or this is the size. It could be anywhere between 1 millimeter to anywhere. I mean, it's a void basically. Entrained air is in this range, capillary pores is in this range, gel pores is here, intercrystallite pores is here, and waters can be sitting all over the place except of course in entrapped air, except of course in the entrained air kind of particles or phases. So this water is easiest to move out. This water is impossible to move out under normal conditions. This is possibly somewhere in between. So once we talk of how much water can be moved out, we have to go back to some kind of a diagram like this. Remember that water sitting in larger spaces is easier to move out. Water sitting in smaller spaces is more difficult to move out. Keep that in mind when we study other characteristics of concrete as well. This is another representation of the pore size distribution and the pore spaces within concrete. The gel pores, the capillary pores, entrained air and entrapped air. As far as concrete is concerned, most of the space is occupied by capillary pores. In fact, this cumulative pore volume exactly shows that. From here to here, this amount of volume is occupied by the capillary pores, which may range from here to here as far as diameters are concerned. And it's important therefore to understand the properties of the capillary pores, and that's something which is beyond the scope of our discussion here. Suffice to understand for you that yes, there is a region of pores which is more important than the other regions, and the pores in concrete are not necessarily all of the same size. They may be saturated with water, not saturated with water. The water present in them may move out more easily, less easily, may never move out at all, and so on. This again is just a recap. Entrapped air is unintentional air in concrete. Entrained air is intentional air through chemical admixtures. Capillary pores exist in the cement paste and at the aggregate ITZ. Gel pores exist within the gels of the hydration products, and intercrystallite water or pores exist within the gel itself. Let's try to understand some of the concepts that we've covered today through an illustrative example with a pore structure, pores being taken as cylindrical, associated with a diameter and a volume. Let's take cylindrical pores having a diameter of D3 and they have a volume associated with them, let's say V3, which means that we need to have a certain amount of length associated with it. We can take it as L3 and we'll get a volume V3. Similarly, for D2, length L2 and we'll get a volume V2. For a diameter D1, we have a length L1 and we have a volume associated with them as V1. We try to take a pore structure with the following details. We are conceptually extending what we did in the previous slide now. There is a D1, D2, D3, D1 less than D2 less than D3, lengths associated such and such, the numbers associated with them so much, and we'll have certain volumes associated with them. Now it's always possible that we try to draw this diagram. That is, the volume associated with the pores having an equivalent diameter of D1, volume associated with pores having a diameter D2, and a volume associated with pores having a volume D3. The way I've drawn it, D3 has the maximum volume, V3 is larger than V2, which is larger than V1. That's not necessarily true, as we will just see in a discussion subsequently. The total pore volume in this situation is V1 plus V2 plus V3. So there's no denying that. If we have a pore structure the way we just saw it, in terms of the diameter and the total lengths, we can calculate the equivalent volumes or the volumes for different diameters and draw this kind of a diagram. Now we can draw for another material, B. We can do the same kind of discussion here where the volume corresponding to D3 is the smallest, the volume corresponding to D2 is the largest, and the volume corresponding to D1 is somewhere in the middle, taking thereby or maintaining therein the total pore volume still being V1 plus V2 plus V3. So it's all the same. So the total pore volume as far as materials A and B are concerned, that is the same, except that the volume is distributed differently as far as the pore sizes are concerned. This adjustment can always be done by doing something with the numbers of pores and the lengths and so on. So that's not so difficult for you to understand, and I'll leave it at that. Now, having said that, this is what we have done. So we have pore structure A and a pore structure B with D1 less than D2 less than D3. What are the kind of conclusions that we can draw from here? The total pore volume in both cases is V1 plus V2 plus V3, except that here V1 corresponded to pores having diameter D1. Here V1 corresponds to the pores having diameter D3. Here V3 corresponded to the volume of pores with diameter D3. Here V3 corresponds to the volume of pores having diameter D2. So the total pore volume in both cases is V1 plus V2 plus V3. In A, the large size pores occupy the largest volume. That's very clear. V3 is the largest. So here the larger pores are contributing greater or more to the total pore volume. In B, the largest pore volume or the largest volume is occupied by medium sized pores. In A, the small size pores occupy the least volume, which is here, compared to B. As of course clear, in B, the large size pores occupy the least volume. Now, I'm leaving it to you to think as to what will be the implications of these comments that we have made in terms of the properties of these two materials. Properties in terms of strength, let's say, and permeability, the ease with which water will move in these two materials. This is something which we need to ponder about. Basically, what we have discussed so far is that parameters that can characterize the pore structure in a material like the HCP or the concrete, there are two. One is the total pore volume and the other is the pore size distribution, which is given as PSD, or the differential pore volume, that is DPV. So the differential pore volume is nothing but how much is the pore volume corresponding to each diameter. The sum of that gives you the cumulative pore volume, and the total finally gives you the total pore volume. Having said that, let's try to look at a slightly different aspect. A concept which we have not touched is the issue of connectivity of pores. This picture here shows some kind of pore structure in a solid. So this is the solids that I have, and these are the pores. So these are all interconnected pores, but there is always a possibility we'll have these kind of pore spaces, because at the end of it we are talking about hydration products. So it's not that we have created, the material will get naturally created, and these kind of pore spaces, if they are formed, these are not connected to the main pore structure, and it's very difficult to measure the porosity or account for these non-connected pores when we are trying to do any studies relating to porosity and the porous structure of a solid like HCP. This is central to our understanding of any porous material. This is something which we must understand, that there could be, or there are, continuous pores of different diameters, and then within that solid we could also have discontinuous pores. The connectivity is the one property which facilitates movement of material within the porous material or that solid. So HCP is a solid, but there are pores through which deleterious material, water, chloride ions, carbon dioxide, all of it moves as far as concrete is concerned, and the connectivity facilitates it. So if the pores were not connected, there were discontinuities, then the material movement within the concrete would be much lower. So that's something which we need to keep at the back of our mind when we try to understand porosity and try to study properties related to porosity, such as permeability or movement of material through the solid. So porosity basically is a measure of the void space in the material. It's a fraction of the volume of voids to the total volume, that is VV by VT. And it could be defined obviously therefore in terms of cc per cc or cc per gram. And it can be expressed as a ratio between 0 and 1 or as a percentage. And we use a technique called porosimetry to measure pores. Study the pore sizes, the volume, the pore size distribution, the density, and the other porosity related characteristics in the material. So porosimetry is the science, and I think we'll take an example now of how this porosimetry is actually carried out. This is an illustrative example again. Consider a pore system as shown with diameters ranging from D1 to D4. Of course, being a 2D representation, the areas here represent the volume. So this is the solid space that we have. The diameter D1 is greater than the diameter D2, greater than diameter D3 and D4. These lengths will give us the areas in this case and can be used to translate this area into the volume. So we can again talk in terms of how much volume is associated with pores of diameter D1, the volume associated with pores of diameter D2, D3 and D4. So once we are able to do that, then what we try to do is to try to push mercury into this pore, and that is the principle of mercury porosimetry. That's one of the methods that is used to study the porosity in HCP and concrete. Now the ease with which the mercury goes in is inversely related to the diameter of the pore. So if we increase the pressure, or we have to increase the pressure in order to ensure that the mercury penetrates into smaller pores. And this is the equation that governs or tells us about the diameter of the pore which will be filled for the pressure that we apply. Of course, the assumption is that the pores are cylindrical, and when the pore diameter is small, high pressure is needed. Measure both the pressure and volume of mercury intruded in the sample. We'll quickly see how it is done, and the pore diameter can be calculated using this equation. As a result of that, the pore volume with a certain diameter can be obtained. So we'll try to study this part of the discussion here in the next couple of slides with, again, illustrative examples. This is the picture of a mercury porosimetry cell. We use our HCP here, which is a very small sample, 1 centimeter by 1 centimeter, maybe sometimes even smaller. Fill this cell with mercury, and then as we apply the pressure, this mercury moves away. That is, this mercury which was here moves down to this place. Now, where did this mercury go? It went into the sample that we have. And once we know what pressure we have applied, we know that equation, then we will say that, okay, this is the amount of volume of pores which will get filled in this material at pressure P. We go to the next pressure step. Again, a certain amount of mercury will be intruded. Let's say it's that much. And this amount of mercury is now filling up the smaller pores. Next amount of mercury is filling the even smaller pores, and so on. So long as we measure both the pressure applied and the volume of mercury intruded in the sample, we can obtain the pore volume and the pore size distribution within the sample. Now, having said that, this is what we really do. We keep applying pressure from the low end to the high end, and we keep getting volumes of mercury intruded. The volumes of mercury intruded, V1, V2, V3. The pressure is being changed from P1 to P2 to P3 to P4. At P1, some D1 is there. That's one number. When we go from P1 to P2, in this range, all the pores between diameters D1 and D2 will be filled, and therefore the average diameter for this would be taken as D1 plus D2 by 2. So that's how we determine the cumulative pore volume using mercury porosimetry, and this is one of the pictures that we have for a cement paste of water cement ratio 60% at an age of 1 day. So you can draw your own conclusions. There is a lot of information that needs to be given to you in order to be able to make meaningful conclusions from here. So this is just an illustration of how this cumulative pore volume looks like with respect to the pore diameters. Now, this mercury porosimetry as a summary is based on causing mercury to fill the voids in the sample by applying pressure. The pressure required increases as the diameter of the pores to be filled reduces. It's easier to fill pores of larger diameters, and that happens at lower pressures. Lower pressures, higher diameters, higher pressures, lower diameters. By measuring the volume of mercury intruded at a given pressure is therefore a measure of the pore volume corresponding to that diameter. And operationally, the measurement works as follows. Create a vacuum in the pore system, push the mercury in steps, increase the pressure gradually, use a pressure time table, and note the amounts of mercury or the volumes of mercury intruding into the pore system at different pressure levels. This discussion of applying pressure in steps and measuring the amount of mercury intruded is analogous to how we do a compression or a tension test. In this case, that is in the case of compression or tension tests, the load is applied gradually and we see the response in the specimen in terms of deformation. But here what we do is increase the pressure gradually with the pressure time table and measure the volume of mercury intruded. So this is what is given here in words. I just said that in the case of porosimetry, the pressure is increased as an independent variable and the response in terms of mercury intrusion is recorded at each step. And as the pressure is increased from a lower to a higher level, the pores are filled in sequence from larger diameters to smaller diameters. Now this is all very nice. What it says is that so long as we start filling the pores from here, the larger diameter, the smaller than that, smaller than that, smaller than that, we will keep getting differential pore volumes and we will get the total pore volume as far as this system is concerned. So this is what we will get. We'll get the pressure, we'll get the volumes, we can get the differential pore volumes, how much volume was intruded in the diameter D1, D2, D3 and D4, the way we've shown it. D1 and the pores corresponding to D1 are the largest, but this is schematic representation. So if we sum this up, we'll get the cumulative volumes. As the diameter becomes small, gradually from the surface to back. Now this is something which we have assumed, that as mercury is being intruded, the smallest diameters are sitting conveniently hidden at the back, and here we have a larger diameter than this, here we have a larger diameter than this, here we have a larger diameter than this. So the diameters are very nicely arranged, and that's what's the beauty of a presentation. I can put my diameters or the pores any which way I like, and we will get a pore size distribution the way it is shown. In a real situation, however, that may not happen. We may have some diameters sitting here with D2, or some pores sitting here with a diameter D2, D3, D1, D2 again, D4 here and D1 here. Now in this kind of a situation, how will mercury porosimetry work? What is the kind of thing that will happen? What will happen is that when the pressure is P1, which would have normally filled a diameter of D1, mercury will not intrude in the sample because the first diameter that it encounters is not D1 but D2. Having said that, further, when the pressure is increased to P2, which corresponds to the filling of pores with diameter D2, the mercury intrudes into the sample for the first time and this space gets occupied. In the next pressure step, when we go to P3, it's not only this diameter or this space which is getting filled, but also this and this, because these diameters are larger than this. The pressure being applied is for this diameter. Obviously it will fill these two diameter pores also, and that is an error. This is not the real pore size distribution. This entire volume here, this entire volume here is getting counted as if it was D3. Similarly, in the next pressure step, when it comes to D4 corresponding to P4, this volume will also get counted as if it was a D4 pore. So this is something which is a bottleneck here. Now this is something which we should keep at the back of our mind, try to understand this effect as far as mercury porosimetry is concerned, this kind of a limitation. And this limitation is called the ink bottle effect. I'm not sure how many of you have used fountain pens and you're familiar with an ink bottle. It used to be something like, it used to look something like this. And there was a mouth here. The diameter here was much smaller than the diameter of the bottle here. That is precisely what is happening here. So this small mouth here with a larger diameter here gives us erroneous results. But then that's the best that we can do, and therefore we live with it. This slide here shows pictures of the mercury porosimetry in actual practice, the actual experiment. We can see here some samples which have been taken off from a hardened cement paste. This is the cell that we talked about. These cells have this thing here, that is the cell, this is the stem, and the samples are placed inside this stem, and these cells are placed inside this machine here, locked up, and then mercury is filled into these cells, and finally the pressure is applied to make sure or measure how much mercury intrudes into the samples which have been placed inside this cell. Now with this kind of a study, we get this kind of distributions. This here is the cumulative distribution, that is the cumulative pore volume, and here is the differential pore volume. It's a matter of detail that sometimes we use the log scale to plot some of these numbers. Bear in mind, and if you read this kind of literature, please be careful how the authors talk in terms of the ink bottle effect and interpret the results from mercury porosimetry for hardened cement paste. There are other terms that are used in this context. Sometimes we talk in terms of a median pore diameter or a D10, and I'm leaving it to you to think about it, to determine or find out the definitions of a median pore diameter or a D10 when it comes to the porosity and pore structure of hardened cement pastes. And obviously you will find that the hardened cement paste, the pore size distribution and the cumulative pore volume, they are a function of the water cement ratio, the kind of cement that we use, and so on and so forth. Let me conclude by saying that hydration as a process leads to two things. One is a reduction in the total pore volume, and the other is a refinement of the pore structure. We'll probably spend some more time in some other class in explaining these two, but I'm sure a lot of you actually understand what these two things mean. And with that, I'm coming to an end of the discussion today. It has been a long discussion, and I must express my gratitude to all my teachers and students, friends. Thank you once again, and I look forward to continuing this discussion with you on special concretes.